So welcome back everyone to our afternoon session. Today we are very happy to have Renzo Cavalieri from Colorado State University who will speak to us about pseudo-stable Hodge integrals. So please.
Thanks, Ethan. Thanks, the organizer, for having me. It's a great pleasure to be here. I want to start my talk by heeding to the advice of Professor Esteves and start with giving the narrative of this talk. Right? So hopefully the narrative that will come across is that the tautological intersection theory of moduli spaces of curves plays well with the minimal model program. Okay, so we've heard from Paolo Cascini a few days ago that the minimal model program is one of the sort of most important programs in algebraic geometry that is aiming to answer the fundamental question of classifying varieties up to birational equivalence. I'm not going to say too much about what the minimal model program for moduli space of curves is, but I want to use this as a motivation to say that, okay, this is worth investigating. There's something interesting going on. And since I'm not assuming that I'm giving this talk to my usual group of moduli space of curves junkies, but a more general audience, I will spend a little bit of time just introducing moduli spaces of curves and what I mean by tautological intersection theory. And finally, by plays well, this is not a very mathematical expression, but what I mean is that I want to show that there is structure in these intersection theoretic computations that this structure reflects the structure of the birational transformations that happen in the minimal model program, at least in the first, the first wall crossing, which is the one we're going to be exploring. Okay? So without further ado, let me start with introducing moduli space of curves, MG and bar. All right? So this is the moduli space of genus G, n-pointed, stable curves. Okay? And so these are curves. Being stable means that we allow them to have very mild singularities, only nodal singularities and finite group of automorphisms. And the genus is the arithmetic genus of the curves. And we decorate these curves with n distinct mark points that are all have to be on smooth points of the curves. Okay? This is a beautiful, rich, sophisticated space. So there's no hope to get very much in depth, but there's a couple things that I want to say that will already help follow a lot of how one can approach studying the intersection theory of this space. So, and I should say not of this space, but these spaces, because as I vary G and N, I have a whole family of these spaces, right? And these spaces are stratified, and they're sociable. Okay? So by stratified, I mean that I have a stratification by topological type of the curves parametrized. Right? So this is a space whose points correspond to, complex analytic structures on one-dimensional subvarieties, or algebraic structure on curves, or hyperbolic structure, whatever you want. But it has an equivalence relation which is a lot weaker than the topologically equivalent relation. So what we can do is you can say, well, let's look inside here at all the algebraic curves that topologically are homeomorphic to each other. Right? And this decomposes these spaces into a disjoint union of locally closed subsets. And sociable, by this I mean that there's a wealth, a lot, of natural morphisms connecting the various moduli spaces. Okay, so, for people that have never seen this before, this might still not be very, very satisfying. So let me illustrate both of these characteristics in just a very simple example that I can do basically completely. I want to look at M1, 2 bars, so the moduli space of genus 1 curves with two distinct mark points. This is it's a surface, it's a compact surface. And it has a open dense set, a unique codimension 0 stratum, whose points parameterize smooth curves with two marks, 1 and 2. Right? Then I have two one-dimensional strata, one that I'm going to call sigma, that parameterizes curves where I basically have a smooth elliptic curve with a rational curve attached to the node, and the 2 points are on the rational curve. I have another stratum, one-dimensional stratum that I'm going to call delta naught, that parameterizes nodal curves. So these are curves of geometric genus 0 but arithmetic genus 1 with two mark points. And then we can see that at the intersection of the two strata, the two one-dimensional strata, or at this sort of self-intersection point of the strata, we have zero-dimensional strata. This one corresponding to basically a rational curve, so geometrically genus 0 curve would attach another rational curve with my 2 points, 1 and 2, and this other point here correspond to what are called the banana curves for hopefully obvious pictorial reasons. Okay, so any questions so far?
So what is the surface? Can you say exactly what it is?
Not off the top of my head, but I believe that people know what it is. Yeah. I mean, I guess it's an elliptic fibration over M11 bar, right? And then M11 bar has an orbifold is P46. So, yeah. Okay. So I think this question was not planted, right? But I think it illustrates the point that one can actually say, well, hopefully I'll be able to say a lot about the intersection theory of this thing, even though I actually don't know what surface it is in any sort of more classical way, right? So this is an example of the stratification and how it works. An example of the sociability of these moduli spaces is that, if you hand me an elliptic curve with 2 mark points, what I can do is I can take the second mark point and throw it away. And what I'm left with is an elliptic curve with 1 mark point. Right? So you can forget some of the points, and what that lands you in is an MG n minus 1. right? So I have down here a map to M11. I'm going to call F2 for forget the second mark point, right? It's not canonical. Well, let me make it canonical by saying that this 1 is actually the set label 1, right? Because but what you're saying is absolutely correct in the sense that I have two maps from M12 to M11. I can forget the second mark point, or I can forget the first mark point, right? And so there is an example of this sociability of morphism. So these are called forgetful morphisms, okay, where you forget some points. Another example of sociable moduli spaces is if we look at the strata, right, you see that they parameterize curves that break up into simpler curves, right? So what is, how do I describe an element of this stratum sigma? Well, I have to give you an elliptic curve with a special point and a rational curve with 3 points, and I tell you to glue the third point of the rational curve with the point of the elliptic curve, right? So this stratum is the image of what's called a gluing morphism from M11 cross M03. Okay? And in fact, every closure of every stratum, right, which I'm going to forget to call, say, closure of stratum. From now on, every time I say stratum, I'll mean closure, because we're going to be doing intersection theory. So every stratum is the image of some gluing morphism, and therefore is the image of some map for some product of other moduli space of curves. Okay? So, any questions so far? All right, so the goal of intersection theory is to understand a space by understanding its subvarieties and how they intersect with each other. Okay? And let me, immediately be, a downer and say the intersection theory of MGN bar is hopeless. With our current state of the art of knowledge of mathematics, we can maybe fully understand the intersection theory of, M1 ends for small n's, M0 ends, and that's it, right? Maybe N2 something, right? But MGN bars, they become very quickly spaces that are too complicated to fully understand their intersection theory. And so Mumford, let me add tautological here. So Mumford in 1983, he proposed an approach where he said, okay, why don't we try to study a subring of the intersection ring of MGN bar, right? Let it be Chow or cohomology or whatever your version is. A subring which, on the one hand, is small enough and simple enough that we have some hope of understanding it. On the other hand, is rich enough to tell us something interesting about the geometry of MGN bar, right? And this subring is called the tautological ring, and Mumford said, okay, let's think about what are the minimal requirements that we could ask this subring to contain, or these subrings for all, one for every G and N. Right? And the minimal requirements is, well, they should contain all the fundamental classes. Right? If we don't have fundamental classes, that not much that we can do. And the second thing is, well, this system of subrings, for all G and N's, should be closed under push forwards and pullbacks via tautological morphism. So forgetful and gluing morphism. Right? So closed under push forwards, pullbacks via natural morphism. And so, as a consequence, immediately, strata, we get strata classes, right? Every stratum is the image of a tautological morphism fundamental classes are in there, and therefore, the whole boundary strata are examples of tautological classes. But in fact, what's somewhat surprising is that there's a lot more than just boundary strata in there, and in fact, a lot of sub-loci of the moduli space of curves that are described in ways that are completely different from coming from this boundary certification end up being tautological, right? Many loci of curves, for example, Hurwitz loci, where you say all the curves that admit a map to P1 of a certain degree, right? These end up being tautological, and that's sort of remarkable. But that's another story. I want to focus on some other classes that are tautological, maybe not immediately so, but where it's not so surprising.
So when you say tautological, you mean the smallest subring that
Yeah. So let me write it. So this is the smallest system of subrings, right, of the union of the chows of MG and bars for all G and N. Yeah. I think that you can. I think Mumford did. When he did it over Q, because then you say I don't have to worry about the fact that MG and bar is a Deligne-Mumford stack. The Q coefficient subring of a Deligne-Mumford stack is the same as its coarse moduli space, so we don't care about it. I think that at that time, 1983, sort of the z-coefficient chow rings of a stack was still a little bit not quite clear. Now we have work of Kresch, Edidin, and Graham. So I think that you could, in principle, repeat Mumford's program with z-coefficients. I'm not a...
Implication would be a theorem, right?
Huh?
This implication would not be completely accurate.
This implication would not be obvious because these maps sometimes have degree which is strictly greater than 1. Absolutely, yeah, absolutely. Yeah, so I am not aware of anybody that has taken this approach of saying, okay, let's work with z-coefficient and see. There's also very little we know about torsion classes in these rings in general, but that'd be great. Cool. Any other questions? Okay, I want to introduce a couple family of classes on this that are tautological, and one way that you can define classes on moduli spaces is to construct bundles on moduli spaces and then take Chern classes, for example. And the way that you construct bundle on moduli spaces is to try to attach to every object parameterized some kind of vector space that comes from the geometry of the object, right? So let me give a specific example and then say what I mean, right? So if I have a curve with a bunch of mark points, what I could do is I could look at the cotangent space of C at the ith mark point. And then I can say, okay, as a moduli space junkie, I would say something very imprecise, which is, therefore there is a line bundle over the moduli space MG and bar called the ith cotangent line bundle, such that the fiber over every point, parameterizing a curve with n mark points, is the cotangent line at the ith point. And which, of course, it makes no sense literally, right? Because a vector space is a vector space, a vector space. They're all isomorphic. You're never going to describe a bundle by just telling what the fibers are. But in this case, telling you that it's the cotangent at the mark point is telling me how these lines will organize in families, right? So if instead of a single curve, I have any family of curves where this point, so this is just one particular fiber here, and this ith point corresponds to a section, right? I can describe the locus of all these cotangent lines as the relative conormal to this section, for example. And so I have some global structure, right? So I have a line bundle over moduli space of curves whose fiber over a point is the ith cotangent line. And then I'm going to call psi I, in definition, the first Chern class of these line bundle. Okay? And it's not obvious, but it's actually, this is pretty simple to show that this is tautological. Classes like this enjoy some nice properties with respect to the boundary stratification. For example, if I take the psi ith class and I intersect this with a boundary stratum where I split my curve into a genus G1 and genus G2 curves, and the points split in a certain way, but the ith point is here, right? Then this is the same, this is equal to the pullback from the first factor of the psi I on the curve of genus 2 in this case. Right? And why? Well, because the cotangent space at the ith point is something that really sees very locally around the ith point. So if everywhere in the locus that you're looking at, your ith point lives on a genus 2 curve where the node is very, very far away, well, this cotangent line bundle is the same as the cotangent line bundle on this moduli space of genus 2 curves with fewer points. Okay. So we know how to restrict psi classes to the strata. Another family of tautological classes are obtained from what are called the Hodge bundle. This is a rank G bundle over MGN bar. And let me again cheat and tell you what this bundle is by telling you what the fibers over a curve is. So the fiber over, let me say a smooth curve, is H naught of C KC, or omega 1 of C. Right? It's the vector space of holomorphic one forms on the curve or the global sections of the canonical bundle. And if the curve is nodal, you have to tweak it a little bit. It's going to be the global section of the relative dualizing sheaf or forms with poles and some residue conditions, but that's not so important. Huh? For any choice of points, yes. So in particular, the Hodge bundles, if you want, they're born on MG bar and then they're pulled back via forgetful morphism as n grows. Yeah, absolutely. Thanks. And I can define tautological classes, lambda I, to be the ith Chern class of the Hodge bundle. And the Hodge bundle also, for how it's defined, it satisfies some nice combinatorial property with respect to the boundary. And actually, I needed to do something here that I forgot, which is to say that because, especially in my circles, people don't like to draw like little surface pictures very much. There's a combinatorial way to identify this strata, which is to draw graphs, the dual graphs of the curves, right? So, which means to put like a vertex for every reducible component of the curves, a half edge labeled by the mark for every mark point, and a compact edge for every node, and this edge becomes a loop if it's a self node. Okay, so I'm going to start using these graphs now to identify boundary strata, even though they're not as pretty, because it's going to be more efficient from now on, right? So if I
So do you also report the genus there?
Oh, yes, sorry. Of course, I chose an example where the genus is 0. And so, yeah, so if the genus is 0, often people will just draw a dot. But if the genus is higher, that's not contained, it's not information which is contained just in the graph, so you have to record it. Thanks. Which would have appeared right now, because what I was about to do is a dual graph with genus. Right? Say that I restrict the Hodge bundle to a nodal, the locus of curves that have one node and genus G1 on one side, genus G2 on the other, then this splits to as the sort of direct sum of the Hodge bundles on the MG1 and the Hodge bundles on MG2, right? So you pull them back from the two projections on the stratum, and then you direct sum them. That's why I have this boxy direct sum. Okay, and let me say another interesting thing about the Hodge bundle is that if you direct sum the Hodge bundle and its dual, this ends up being a flat bundle, right? And therefore, it has no Chern classes. The total Chern class of this rank 2G bundle is 1. And so in particular, we have, this, I could expand it out as 1 plus lambda 1 plus dot 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 plus lambda g times 1 minus lambda 1 plus lambda 2 minus dot 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 plus or minus lambda g. And so for every even degree, I get a relation. Something not obvious, right? For example, in degree 2g, we have that lambda g squared is equal to 0. And all the way to the other extreme, right, in degree 2, I have that 2 lambda 2 minus lambda 1 squared is also equal to 0. So we have a lot of nice relations. Okay, so now a Hodge integral is an intersection number of lambda and psi classes. Okay, so I can intersect a bunch of these classes until I get to sort of something of top degree. I can integrate and count and get a number of points, right? So these are some sort of, if you want, virtual enumerative objects. Right? Counts. And let me write, these are very pretty things to work on and compute, and let me just write a couple examples to show. So these are from Faber and Pandaripande. So if I look at the integral over mg1 of psi to the 3g minus 2, right? This is equal to 1 over 24 to the g times 1 over g factorial. And if I look at the integral over mg1 bar of lambda g psi to the 2g minus 2, this is equal to 2 to the 2g minus 1 over 2 to the 2g minus 1, b2g, where this is the 2g Bernoulli number, over 2g factorial. Which, again, if you like Bernoulli numbers, this looks already cool. If you don't like Bernoulli numbers and you ask yourself why do Bernoulli numbers arise, it's because there's enough combinatorial structure here that if you were to take that these numbers satisfy some recursion, so that if you package them in generating function, a generating function of these numbers, let me call this C sub g. C sub g t to the 2g ends up being something like t over 2 divided by sine of t over 2. Right? So one way to say, well, these numbers have a lot of structure is that they satisfy universal relations that become differential equations on generating functions that are simple enough that they have solutions that we've studied in trigonometry or in calculus. Okay? Okay. So any questions about stable Hodge integrals? Okay. So I want to now switch from stable to pseudo-stable.
Sorry, I have a question, but is it obvious that you have this germ classes treatment?
This one, it's obvious in the interior. It's not completely obvious on the boundary when you close it up on OMG and bar, but it's true. Exactly, exactly. Then Mumford showed that this actually extends to the boundary. Yeah, thanks. All right, so the minimal model program tells you, okay, well, no, it's talk to Paolo about the minimal model program, and you'll find out that after you cross the first wall, what happens is the moduli space MGM bar undergoes a birational contraction. Right? So what happens is that you get another moduli space called a moduli space of pseudo-stable curves. And this pseudo-stable curves, basically, it means that you do not allow curves with elliptic tails. But you allow, and in fact you replace them, cusps as singularities. Right? So in this example right here, let me erase here. M12 pseudo-stable, what happens is that we don't like any curve that looks like this, right? And so we get rid of them, but we allow curves that have a cusp, right? So there's going to be this whole green line gets contracted to a point corresponding to a curve with a cusp. And that's really the only thing that changes. And yes, and the number of automorphisms is finite. Okay, that's it. And there is a regular contraction, tau. And so then one can say, okay, I can define psi classes, I can define Hodge classes on these pseudo-stable spaces. I can compute intersection numbers. How do they differ from the corresponding intersection numbers on MG and bar? Okay, that's the question that we set out to study. Okay, so let me start saying some results. So the first result, I'm not even going to write it down, which is if you have a psi class here, and you pull it back, and you say, how does it differ from the corresponding psi class up here? It doesn't. Why? Because just like before, mark points could never be singular points. Right now, mark points could never be cusps. And so the cotangent line did not notice that I squished something, right? So psi classes, they pull back. And so if also lambda classes pull back, then the answer would be like, well, the intersection number by projection formula are exactly the same, and this would not be an interesting problem. Okay? But lambda classes do not just pull back. And so, theorem. This is myself, Gallegos, Ross, Van Over, and Wise. And it just appeared in 22. And so we said, OK, what happens when you pull back the ith pseudostable lambda class? Well, this has this, well, I think, pleasing expression. The summation from 0 to I of 1 over k factorial. And then I have the kind of the flying spaghetti monster here. This is a boundary stratum corresponding of a curve with k elliptic tails, right? And I have the lambda I minus k class pull back from the factor corresponding to the g minus k component. Right? So this is saying that this starts as lambda I, but then it gets these corrections, right, on the locus of g minus 1 curves. With one elliptic tail, I have lambda I minus 1, and so on and so forth. Okay, so the relation, I mean, they don't pull back, but the correction is very combinatorial. And as a corollary, of this formula, this all Hodge integrals with exactly one Hodge part and arbitrary many psi's agree with their pseudo-stable counterparts. Okay. So again, lambda classes pull back in a way which is somewhat interesting, non-trivial. But at least for intersection numbers where you only have one lambda class, nothing exciting happens. And this is something that, if I were not running out of time, I had planned to show the proof is actually very simple, right? But so I want to bring in my grad student, Matthew Williams. I told him, OK, why don't you explore the case with two Hodge parts? And in particular, I wanted to ask him, what happens to the Mumford relation in the pseudo-stable case? We already knew, we had observed with this group of people that the Mumford relation did not hold. But is it nice? How does it break? How badly does it break, right? And so, and this is Matthew's theorem. Let me write it down here. Myself and Williams, and hopefully it will appear this year. Let's say 23. Right. And so what happens if I pull back the total Chern class of the pseudo-stable Hodge bundle plus the dual of the pseudo-stable Hodge bundle? Then what I get is the summation from t to the k over k factorial. And on the stratum with g minus k on one vertex and k elliptic tails, I have the product from I from 1 to k of psi star minus psi star I minus psi dot I, where the stars and the dots are the mark points corresponding to the two shadows of the node where you attach all the elliptic curves. So again, the Mumford relation fails, but it fails in a very sort of controlled and combinatorial way. Right? And so I'm out of time, but let me just say with words in 30 seconds what I was planning to show if I had a few more minutes. So you start observing that there's some strange things. So if you look at this on the pseudo-stable case, instead of this answer, you get 0. And I mean, you start seeing some strange correspondences between quadratic, stable, and pseudo-stable Hodge integrals. And let me just get to the punchline. At the end, if you write down a generating function for pseudo-stable Hodge integrals and a generating function for stable Hodge integral, and you want to compare them, you can compare them simply by multiplication by an exponential function. Right? So this epsilon is the genus parameter. And then you're going to have a bunch of other formal variables that keep track of, besides the genus, the mark points and the powers of psi classes and the lambda classes, the two lambda classes. And what we notice is that really the only thing that you need to use to correct, the information that you need to use to correct from stable to pseudo-stable is the genus parameter. And so this is, to me, a beautiful structure result. And I'll stop here since I'm a little over time. Thank you.